Fact 1. The term artificial intelligence was first established in 1956. This event took place at a summer school in Dartmouth, where John McCarthy put forth the name for this domain, envisioning machines that could learn any aspect of intelligence. However, the actual implementation started somewhat earlier. In 1950, Alan Turing proposed a test designed to ascertain the indistinguishability of machine-generated answers from human ones. In 1956, Newell and Simon showcased the logic theorist program, which could prove theorems. And in 1958, Frank Rosenblatt introduced the perceptron, a straightforward model for recognition that could learn. Following this, there were phases of progress and periods known as AI winters. These phases were marked by exaggerated claims and decreases in funding during the 1970s and the late 1980s, alternating with fresh advancements. This cyclical pattern is an important element of its narrative. Expectations tend to become overly optimistic, after which methodologies are honed, and then data and computational resources align with the initial aspirations, resulting in a stronger revival. The second fact is that a modern neural network is structured as a cascade of linear transformations and nonlinear elements. Within it, millions and billions of numerical weights are fine-tuned for a given task. The training process works like this. The network produces a prediction. A loss function measures the error. The backpropagation algorithm calculates the specific changes needed for each weight, and stochastic gradient descent takes a small step toward an improved solution. Activations, such as ReLU, have hastened the training of deep layers. Regularization, like dropout, and normalization methods have stabilized gradients. Many batches and optimizers like Atom have introduced flexibility. Models are trained on GPUs and specialized accelerators, TPUs and their counterparts, where thousands of cores perform parallel matrix multiplications. An important point is that training and inference are distinct modes. Training is data and energy intensive, while inference is optimized for speed and cost-effectiveness. The third point is that the synergy between transformer architecture and scaling proved to be a decisive factor. In 2017, the concept of attention was put forth, a mechanism allowing models to evaluate links across any input components, circumventing recursion and convolutions. This dramatically streamlined parallelization and unlocked the potential for extremely large models. Subsequently, empirical scaling laws became evident. As parameters, data, and computational steps grow, validation error diminishes following a power law relationship. This predictable decrease continues as long as sufficient quality data is available. This dynamic spurred a pursuit of more tokens, expanded context windows, specialized domain fine-tuning, and chain-of-thought training. Discussions persist regarding the emergent abilities observed in large models. While some outcomes are attributed to a smooth quality progression and task-specific thresholds, the fundamental reality is that scale continues to offer substantial advantages for the foreseeable future. It is the fourth fact that large language models do not truly know facts. Instead, they predict the next text segment by analyzing statistics from massive text datasets. This gives rise to hallucinations, which are confident but wrong answers, occurring when context is vague or information is scarce. This is not lying, but a result of how generation works probabilistically and the lack of direct access to original sources when answering. To lower this risk, methods like training with human input, RLHF, linking to outside search and data stores, retrieval-augmented generation, setting strict output formats, checking with tools, and verifying through steps, where the model explains its process and those steps are checked, are beneficial. Yet, there's no absolute certainty. The more general the topic and the newer the fact, the more essential it is to check information and use careful phrases like by estimates or based on data from. Fact number 5. highlights that the ethical considerations and regulatory frameworks for artificial intelligence are now on par in importance with the accuracy of AI models. AI systems have a tendency to absorb biases found within the data they are trained on, including biases related to gender, race, and cultural backgrounds. Without implementing measures to counteract these biases, the systems are likely to exacerbate them in the decisions they make. In reaction to these challenges, practices such as audits and the development of dataset and model cards, which outline limitations, performance metrics, and potential risks, have become prevalent. The legal landscape is also adapting to technological progress. The European Union has adopted a comprehensive act on AI, which categorizes AI systems based on their risk levels. This ranges from prohibited applications such as manipulative biometrics to high-risk applications in sectors like medicine, finance, and critical infrastructure, all of which are subject to strict requirements for data management and transparency. Nevertheless, critical questions remain unresolved, such as the legality of training AI on copyrighted materials, the protection of personal data, and the allocation of responsibility for harm caused by automated decision-making processes. A standard conservative practice involves maintaining human oversight in the decision loop, alongside thorough logging and verifiability of system operations. Sixth fact. In AI, architecture isn't the only determinant. Data composition is equally significant. Large models ingest the world through a combination of web pages, books, code, dialogues, images, and audio. The quality of this data mix is paramount. Sources that are noisy, toxic, or legally contentious can introduce biases and errors. The data pipeline itself is a distinct engineering field, encompassing collection with licensing and consideration, cleaning, deduplication, filtering by language and topic, domain balancing, and, crucially, controlling test contamination to prevent premature exposure of answers to the model. Synthetic augmentations are frequently employed, where a capable model generates instructions and analyses to train more compact models. However, this necessitates oversight, including checks for diversity and plausibility. The concluding stage involves instruction fine-tuning and alignment for safe responses, where accuracy, tone, established boundaries, and the ability to refuse harmful scenarios are all vital. Seventh fact. Reinforcement learning is a process where an agent learns to take actions by receiving rewards for successful outcomes. A well-known illustration involves programs that outperformed champions in the games of Go and chess. These agents underwent training within simulated environments, repeatedly enhancing their strategic approaches. Nevertheless, the real world presents greater complexity than games. Rewards are often indistinct, surroundings are volatile, and errors can incur significant costs. For these reasons, techniques such as safe exploration, learning through expert trajectory imitation, offline learning from recorded data, and meticulous reward design to avoid incentivizing cheating are utilized. In the field of actual robotics, simulators and the transfer of knowledge to the physical domain are of paramount importance. For recommendation systems, it is crucial to monitor the development of preferences to prevent the system from narrowing a user's scope of interests. Additionally, reinforcement learning is commonly integrated with world models or large language models to facilitate the parallel advancement of planning capabilities and explainability. Eighth point. Computer vision transitioned from manual features to deep networks. The significant advance in image recognition happened when convolutional architectures sharply decreased errors in major competitions. Next, residual connections facilitated the building of very deep networks, and then visual transformers transferred attention to the pixel world. Presently, a single model can concurrently perform object localization, scene segmentation, depth estimation, and pose assessment. However, there are complexities. Domain mismatches, for example, models trained by day have difficulty operating at night. Uncommon situations and sensor shifts weaken certainty. Consequently, benchmarks on distribution tails, synthetic data enhancements, and tests for robustness against weather, glare, and compression artifacts are crucial. In medicine, a second stage is added. A doctor verifies the conclusions, and the system records its confidence and explainable characteristics. Fact 9. Prompt engineering is now a craft. The model's output is shaped by how the task is phrased. System instructions dictate the style and set boundaries. Few-shot examples provide a solution template, and rigid formats like JSON with a schema decrease ambiguity. Integrating tools such as calculators, search functions, and databases positions the model as an orchestrator, choosing between independent thought and external service consultation. The vulnerability known as prompt injection involves malicious code within data or on web pages aiming to override instructions. Defense strategies include isolating context, using filters, verifying sources, and applying a least privilege principle for tools. Furthermore, deceptive explanations can occur. Asking for reasoning might not yield truthful insights. Thus, for critical tasks, concealed reasoning paths and external step verification are utilized. Fact number 10. The AI economy revolves around the pursuit of efficiency. Training massive models necessitates months of computational effort and precise financial planning, including decisions on the number of parameters, data volume, strategies for distributing training across hardware, and methods to minimize idle periods. During the implementation phase, optimization techniques are vital. Quantizing weights to 8 or 4 bits without degrading performance on designated tasks, eliminating less important connections, and distilling knowledge into more streamlined networks. Furthermore, server infrastructure engineering is key. Batching requests, caching attention keys, partitioning data across nodes, and managing traffic priorities. Data centers evaluate not only monetary expenses, but also water and electricity usage, striving to reduce their carbon impact and mitigate overheating. For users, hybrid approaches prove beneficial, where a portion of inference is handled locally and another part in the cloud, resulting in increased speed, better privacy, and cost efficiency when managed effectively. 11th fact. Multimodal models merge text, image, sound, and video into a single format. This allows them to comprehend a scene and communicate about it in human language. The fundamental method is contrastive learning. It works by bringing together an image-caption pair within a shared feature space, while pushing dissimilar pairs apart. Visual data is tokenized by segmenting frames into patches. Sound is processed using spectrograms, and video is handled by appending time markers to frame sequences. Building on this, dialogue capabilities are trained, which depend on pixel information. This includes answering questions about an image, describing charts, and reading interfaces sequentially. This leads to increased accessibility, such as enabling scene recognition for the visually impaired or analyzing medical images with written explanations. However, characteristic mistakes also arise, known as object hallucinations. This occurs when a model confidently perceives objects in a photo that were frequently associated in the training data but are not present. Therefore, verifying the origin of information and checking the model's outputs are mandatory. Fact number 12. Speech recognition has evolved from a process of stitching together acoustic and language models to utilizing end-to-end architectures. For a period, CTC and RNNT served as the benchmark for streaming dictation. Subsequently, transformer models gained the ability to process audio in chunks with minimal latency. The challenges in this field are not confined to phonetics alone, but also encompass environmental factors, background noise, various accents, language interference, proper names, and informal speech. To ensure dependable performance, a combination of domain-specific adaptation, custom dictionaries, and real-time microphone normalization techniques is employed. On the other side of this technological spectrum is speech synthesis. Contemporary text-to-speech systems leverage neural vocoders and diffusion decoders, which are capable of rendering nuances such as vocal timbre, pauses, and breathing sounds. Users can also adjust the speech's style, pace, and emotional tone, with the possibility of voice cloning using just a few seconds of sample audio. While this technology is highly advanced, it also introduces significant risks, including the potential for biometric spoofing and various forms of fraud. This has led to a growing demand for anti-spoofing measures, the implementation of digital watermarks, and the establishment of policies requiring explicit consent for the use of voice data. According to the 13th fact, image and video generation utilizes diffusion processes. The model learns to progressively eliminate introduced noise, converting randomness into a coherent visual representation. Often, this occurs within a latent space. The image is first compressed by an autoencoder to enhance computational speed, and subsequently, diffusion operates on these compact representations. Guidance is provided through natural language prompts, masks for inpainting, depth maps, pose information, or sketches. A technique called classifier-free guidance also exists, allowing for the regulation of how closely the output adheres to the prompt. Video generation introduces the challenge of ensuring frame-to-frame consistency. Optical flow, keyframes, and motion anchors are employed for this purpose. For 3D applications, radiance fields and Gaussian splats are used to maintain geometric integrity. The ethical dimension involves detecting and marking synthetic content, protecting private individuals, prohibiting harmful scenarios, and respecting the copyright of training datasets. Fact 14. The explainability of AI is a group of methods, each shedding light on a segment of its mechanics, but not providing a full X-ray of the entire system. Saliency maps indicate which pixels or words have a stronger effect on the outcome. Integrated gradients measure the contribution of features. LIME and SHAP create local linear approximations centered on a particular example. In transformers, attention heads and activation paths are investigated, sometimes defining standard roles like copying patterns, matching brackets, or following long dependencies. There is also a mechanistic approach, visualizing features, using linear probes, and conducting careful experiments to turn off chains. But an important caution: attention maps are not the same as causality, and a pretty graph doesn't guarantee the conclusion is right. Practice needs benchmarks for explainability, repeating results, and matching interpretations with changes in the model's actual behavior. Fact number 15. The assessment of artificial intelligence is developing into a distinct field. Standard tests for classification and translation have been supplanted by broad examinations that encompass logical challenges, programming tasks, mathematical problems, and sequential solutions with verification of their outcomes. In this context, a phenomenon known as leakage occurs. Models might have been exposed to comparable questions during their training phases. Consequently, the purity of tests, the confidentiality of datasets, and the consistent rotation of tasks are of significant importance. For systems designed for conversation, metrics are incorporated to measure factuality, toxicity, and the ability to withstand provocations and prompt injection attempts. The evaluation of generated code involves executing tests, whereas for images, a blind comparison by human evaluators is conducted, focusing on criteria such as composition and textual alignment. The use of automated judges, advanced models that compare the outputs of less proficient models, is becoming more prevalent, with their own performance being adjusted based on human judgments. It is considered good practice to perform multifaceted evaluations, assessing aspects like accuracy, security, punctuality, and expense during actual operational use. Fact 16. The neurosymbolic approach endeavors to unite the strength of statistical learning with the exactness of logical rules. To put it plainly, a neural network is adept at recognition and generalization, while the symbolic part acts as a letter-of-the-law checker. Do the answers conform to tabular limitations, ontologies, business regulations, or standards? This could take the form of invoking a constraint solver after a plan is created, embedding domain-specific languages, DSL for formulas, or querying a knowledge graph where entity links are clearly specified. The advantage lies in control. It allows for explaining the validity of a solution and also for guaranteeing restrictions. For instance, a patient with an allergy will not be prescribed a drug from the prohibited list. The disadvantage is the interface's fragility. Rules that are too strict compromise flexibility, and those that are too loose fail to provide guarantees. Hence, architectures are designed with layers: recognition first, then verification, and finally adjustment through feedback. Fact 17. Agent systems built upon large language models represent an endeavor to evolve a model from a simple responder into an agent capable of executing multi-stage tasks. An agent is designed to retain its objective, formulate a plan of action, utilize tools like search, code, spreadsheets, or APIs, interpret the results obtained, and refine its subsequent actions. In configurations with multiple agents, roles are segmented. One agent may be designated for planning, another for execution, and a third for verification. A different architecture employs a single agent that engages in a reasoning cycle, supported by a short-term memory of past steps, which is further enhanced by a long-term vector storage system. This methodology is advantageous for integration purposes, spanning from semi-automated RPA processes to the analysis of documents. However, inherent risks include the potential for infinite loops, undue confidence from the model, an inability to deviate from an incorrect hypothesis, and vulnerability to external prompts originating from the data. In practice, guardrails are put in place. Limitations are imposed on the number of steps and the budget, code execution occurs within sandboxed environments, APIs are restricted to whitelisted options, critical actions undergo verification, operations are logged, and scenarios are evaluated offline before being introduced into production. Fact number 18. The privacy and security of AI involve more than just content filters. Attacks like membership inference attempt to identify if a specific instance was in the training data. Model inversion is another attack, trying to recreate original records from a model's feedback. Data poisoning is also a concern, where an attacker inserts harmful data into a dataset, changing how the system works. In federative learning, gradients themselves can lead to leaks, so secure aggregation and differential privacy are employed. Differential privacy adds noise to formally limit leaks, but it might lower accuracy. For systems that are already running, prompt filters, keeping tools separate, and preventing the extraction of secrets from connected sources are important. Safe methods include red teaming, checking for personal data leaks, watching for unusual activity, and having a rule for granting only the necessary rights for each connection. Fact 19. AI is increasingly active at the frontier of science and medicine. Models assist in predicting protein structures and molecular interactions, generating drug candidates, ranking them by properties, and proposing experiments. The cycle of hypothesis, synthesis, measurement is sped up by active learning and automated robots in digital laboratories. In clinical practice, algorithms support image interpretation, identify suspicious zones, suggest likely diagnoses and risks, and help with triage in overloaded departments. However, validation is essential. The transition from retrospective data to real patients often fails, and without clinical trials, oversight, and consideration of gender, age, and ethnic group biases, decisions can be detrimental. The ethical rule stays the same: a human in the loop, transparent application criteria, and tracking the impact on treatment outcomes. Fact 20. AI sustainability is tied to electricity, water, carbon emissions, and hardware. Training large AI models necessitates enormous matrix calculations. Data centers are working to enhance cooling efficiency and lower their PUE. Businesses are shifting their computational workloads to regions that utilize more renewable energy sources. Algorithmic strategies such as quantization and pruning, reusing already trained model parts, distilling knowledge into smaller models, and adapting models using low-rank layers instead of full retraining are employed. For the inference phase, the on-device approach is helpful as it performs some computations locally, which cuts down on delays and network traffic. In terms of hardware, specialized accelerators are becoming more prevalent, and alternative methods like spiking and analog computing are under investigation. These are still experimental but offer promising energy efficiency. Responsible AI practices include budgeting for carbon emissions, scheduling operations when renewable energy is available, and making smart hardware upgrades to reduce electronic waste. Fact 21. Embeddings serve as a technique to represent a word, phrase, code, or an entire page as a point in a multi-dimensional space where the distance between points reflects their semantic similarity. This allows for semantic search. By comparing cosine distances or dot products, we can find items that are close in meaning, not just in spelling. To achieve speed in searching, approximate indexes are created, such as HNSW graphs or IVF with product quantization. Documents are segmented into chunks with overlapping sections to ensure that a search query can locate the relevant paragraph. Real-world issues include hubness in high-dimensional spaces, where some fragments act as universal magnets. Vectors can exhibit anisotropy, requiring normalization. Moreover, general embeddings might not accurately capture domain-specific language. Practical implementation involves query re-encoding, using a cross-encoder for re-ranking, managing metadata, and conducting thorough quality assessments with recall at K and MRR on live tasks. Fact 22nd. Retrieval Augmented Generation, RAG, serves as an external memory. Before delivering an answer, the system retrieves relevant data chunks from an index and places them within the context, allowing the model to draw upon current sources. High-quality RAG is not solely about embeddings. It also depends on a meticulous pipeline. This pipeline involves normalizing and marking documents, defining a strategy for slicing and titling, filtering by specific dates and languages, re-ranking results, eliminating duplicates, and adding markers for citations and confidence. A major risk is prompt injection originating from the retrieved text. Instructions that are inadvertently heard can attempt to alter the established rules. Consequently, it is advisable to use sandboxed environments for tools, implement whitelists for actions, and escape inserted content. To ensure system resilience, caching mechanisms are incorporated. Self-consistency is pursued through multiple queries, extensive text blocks are compressed, and a fallback to web search is prepared. The evaluation process is comprehensive, assessing the correctness of facts, the thoroughness of the response, the percentage of information cited with links, and the efficiency in token consumption under actual usage conditions. Fact 23rd. MLOps for AI is an operational discipline where the model is just one artifact among data, code, and infrastructure. Everything is versioned: datasets, features, weights, containers. Pipelines are built as DAGs with reproducible steps. Deployment begins in shadow, then canary on part of the traffic, then A/B with clear metrics and a rollback plan. Online monitoring tracks P95, P99 latencies, errors, costs, and data. Distribution shifts, PSI, KL, training prod drift, and fairness by segments. Alerts are needed for drift, automatic index rebuilding, periodic benchmark reevaluation. Feature stores and online feature stores reduce drift, and lodging requests and responses creates fuel for retraining. The main thing is processes: security regulations, checks for toxicity and leaks, access control to sources, and regular post-mortems for incidents. Fact 24th. Tokenization is a subtle yet crucial layer that sits between text and the model. Subwords are used instead of letters. Algorithms like BPE or sentence piece gather frequently occurring pieces to split words less often. This impacts everything: how much a phrase costs in tokens, how much context fits, and how the model handles morphology. Languages without spaces, such as Chinese or Japanese, are often more compact in tokens, while languages with many word forms, like Finnish, expand. Byte schemes help with rare symbols in code but break up numbers and math formulas, making computational tasks harder. In multilingual models, a shared vocabulary allows for knowledge transfer but uses up slots on rare combinations. A domain tokenizer for code or chemical formulas is sometimes warranted. In production, it's important to fix the tokenizer version. A change in markup subtly breaks compatibility for prompts and old examples. Fact 25th. In the field of robotics, AI is moving out of the screen and into the physical world. In this physical space, sensors, dynamics, and safety are important, in addition to understanding text. Visual motor policies connect visual input with manipulator actions, and language acts as an interface for setting goals such as, take the red mug and place it to the right of the plate. Training is based on learning from demonstrations. It is further trained in simulation and then transferred to reality through domain randomization, which involves adding noise, friction, and lighting. Tactile and force sensors help prevent objects from breaking, and SLAM and 3D scenes provide localization and trajectory planning. There are strict limitations: real-time operation, dependence on delays, and hard limits on speed and forces when near people. Practice involves a safe stack, stop contours, space zoning, checking goals before gripping, logging every contact, and predictable behavior when vision or communication is lost. Fact 26th. A key weakness for many models is their susceptibility to adversarial examples. If noise, imperceptible to humans and found via techniques like FGSM or projected gradient descent, is added to an image, a classifier will confidently mistake a turtle for a rifle. Even more problematic, these attacks are effective in the physical world too. Stickers on road signs or patterns on shirts can mislead detectors. While defenses are available, none are a perfect solution. Adversarial retraining boosts resistance but often lowers accuracy on clean data. Randomized smoothing provides probabilistic guarantees within a specific area, but this is limited by the area's size. Anomaly detectors can catch some attacks but often produce false alarms. A realistic strategy involves multiple layers of defense: strict input filtering, monitoring for domain shifts, validation using distribution tails, and operational telemetry for early detection of failures. Fact 27th. Models often overestimate their confidence. Low maximum probabilities can signal "I am confident" even when the prediction is incorrect. Calibration addresses this deficiency. Simple temperature scaling on validation data aligns the probability scale. Ensembles and MC Dropout provide an uncertainty estimate by considering the diversity of their predictions. Conformal prediction offers a more advanced solution, returning a set of classes rather than a single one, within which the true class is expected to fall with a given probability. In regression, this manifests as intervals. In production environments, this modesty proves valuable, enabling systems to abstain from predicting, involve human operators, or request further data. However, calibration requires ongoing support. Changes in traffic patterns and new model versions can subtly degrade its performance. It is advisable to perform regular stress tests on infrequent scenarios. Monitor the expected cross-entropy risk, and implement a policy of selective prediction where the cost of an error is explicitly contrasted with the cost of withholding a prediction. Fact 28th. AI operating on a device relates to privacy, latency, and energy usage. Modern phones and laptops incorporate NPUs and sped-up operators that run local models for speech recognition, photo filters, auto-completion, and even basic dialogue processing. To adhere to thermal and power budgets, weights are quantized to 8 or 4 bits, sparsity is used, operations are fused, attention caches are leveraged, and efficient blocks are implemented. Personalization is also a feature. Fine-tuning occurs using a user's own dictionary, voice, or style without raw data being sent to the cloud. Strict limitations exist, including memory, bandwidth, and background tasks. This leads to the demand for hybrid setups, where some logic runs locally and some in the cloud, with intelligent switching during poor network conditions. The front end is also vital. Web GPU and mobile graphics APIs permit inference execution directly within applications, preserving user data control and delivering instant interface responsiveness. Fact 29th. AutoML streamlines the process of hyperparameter and architecture discovery. Methods such as Bayesian optimization, evolutionary strategies, and population learning enhance model quality while the engineer is not actively engaged. Weight-sharing NAS allows for the reuse of weights when evaluating multiple candidate networks, eliminating the need for full retraining. Nevertheless, the actual situation is frequently more challenging. It is easy to overfit to a benchmark, gain insight from validation data, or expend resources on marginal improvements. The current trend involves reducing emphasis on architecture magic and increasing focus on data and its customization. The application of LoRa layers, fine-tuning tailored to a specific domain, and careful corpus segmentation and cleaning provide greater impact at a reduced cost. A robust AutoML framework encompasses not only the models themselves, but also the entire operational workflow. This includes dataset versioning, automated drift detection, index restarts, oversight of experiment expenditures, and the creation of reports following predefined protocols, thus guaranteeing the reproducibility of every achieved improvement. Fact number 30. Graph neural networks learn by using relationships. Nodes are entities, and edges are the links between them. The next step is message passing. Each node collects messages from its neighbors and updates its own understanding. Different types exist, like GCN, which averages, GraphSage, which uses learnable aggregators, and GAT, which pays attention to key neighbors. They are used in many areas: for recommendations, linking users, items, and events; fighting fraud by looking at transaction patterns; in chemistry, treating molecules like graphs; for logistics; and for knowledge. There are also problems. Over-smoothing makes nodes too similar when the network is deep, and over-squashing squeezes information from far away into a small space. Solutions include using skips, jump links, position information, picking parts of graphs, and creating levels. To handle large amounts of data, they use small groups of subgraphs and spread out storage. To make them understandable, they show the important paths and patterns, revealing which links helped the model reach its decision. This is needed in areas where trust is important. Fact 31st. Self-supervision has emerged as a quiet revolution, allowing models to learn from free signals inherent in the data, bypassing manual labeling. In text processing, this translates to masking tokens and recovering omitted elements. For image data, it entails contrastive tasks such as clustering alike instances and separating dissimilar ones, predicting augmentations, or reconstructing degraded patches. For audio, it involves forecasting hidden representations, Wave2Vec 2.0, where the network anticipates future spectral portions. These pre-training strategies establish versatile features that are easily fine-tuned for particular applications, thereby lowering the entry threshold for domains with limited labeled data. Yet, potential issues arise: representation collapse in the absence of negative samples, cheating through augmentation artifacts, and concealed test data leakage during corpus gathering. Practical measures include stringent deduplication, task hybridization, regularization, and mandatory transfer benchmarks on distinct datasets. Fact number 32 explains that continuous learning causes model disruption through catastrophic forgetting. This phenomenon occurs when a network, after being trained on a new task, suddenly loses its previously acquired abilities. To counter this, various types of methods are applied. Regularization approaches, like elastic weight consolidation, safeguard important weights by penalizing substantial deviations. Replay buffers are designed to hold a small sample of past data or their condensed versions. Generative replay generates memories using an auxiliary model. Other methods include architectures with separate heads connected to a common body, and those that increase parameters, such as progressive nets, adapters, and task-specific LoRa modules. In production settings, domain shift detectors are integrated, a canary evaluation policy for existing scenarios is employed, and a budget for avoiding forgetting is maintained. If the decline exceeds a set threshold, training is either reversed or data streams are merged until stability is restored. Fact 33. The goal of causal inference is to determine what will happen if we intervene, rather than what is it associated with. Formal methods are based on directed acyclic graphs, backdoor criteria, and the do operator, which enables the separation of observation from intervention. To establish effects, one must close the backdoor, find instrumental variables, or create propensity score stratification. Counterfactuals extend this by examining what would have happened to the same person if a different decision had been made. In machine learning, this is useful for marketing uplift models, medical A/B tests, and for building explainable credit scoring policies. The limitations are apparent. An incorrect causal diagram can result in false confidence. Unobserved confounding variables distort estimates, and complex interactions require specific domain knowledge. Sound practice combines causal hypotheses, simulations, and the pre-registration of analytical approaches. The 34th point. Generating code with language models has evolved into a functional tool, supporting everything from line completion to function creation from specifications. As code is an artifact that can be checked, the surrounding environment is constructed with protective measures. This includes mandatory unit tests, static analysis, linters, typing, running in a sandbox with limited rights, and an iterative repair loop where a test failure serves as a prompt for fixing. The training's quality is contingent on licenses and the purity of repositories. Secrets, keys, and compromised samples are removed, and copy-pasted or generic code is filtered. Typical malfunctions encompass code that compiles but is logically flawed, insecure patterns, overlooking extreme cases, and dependency on particular library versions. Therefore, in production, human code reviews persist, dependency versions are locked, and success is measured by task closure speed and defect reduction, not by synthetic benchmarks. Fact number 35. Time series forecasting capabilities surpass ARIMA and PROFIT. Transformer architectures, namely Informer, Autoformer, and PatchTST, are designed to learn from extended dependencies and external features, such as weather patterns, promotional activities, calendars, and raw material prices. The modes of forecasting are critical. Short-term horizons are essential for inventory control, medium-term horizons for data center capacity planning, and long-term horizons for infrastructure development strategies. Furthermore, anomaly detection is of paramount importance, utilizing techniques like STL and seasonal trend decomposition, Bayesian change point identification, CUSM, and autoencoders with reconstruction error assessment. The primary risks encountered are data leakage, the incorporation of future information into features, concept drift, and shifts in operational regimes, covariate shift. In practical settings, it is imperative to implement rolling origin cross-validation, construct predictive intervals, factor in holidays and promotional campaigns, and conduct causal retrospective analysis. Interventions, for instance, price caps or lockdown measures, can fundamentally alter the data generation mechanism. 36th point. Human in the loop signifies an engineering requirement, not merely a slogan, for situations involving unclear data. Annotation extends beyond simple cat/not cat labels to include instructions, edge case examples, rejection criteria, and dispute resolution procedures. Quality is gauged by inter-annotator agreement, Cohen's kappa, Krippendorf's alpha, sustained by golden tasks embedded in the data flow and performer calibration. Active learning offers budget savings by having the model propose most useful challenging examples for manual review, speeding up the improvement of decision boundaries. For complex domains, error atlases and taxonomies of contentious cases with examples are developed. Ethics and safety are crucial. Anonymize personal data, filter toxic content, and safeguard moderators' mental health. The process culminates in an iterative loop. Gather, annotate, analyze errors, update instructions, repeat, until metrics stabilize and the production distribution stops creeping. Fact 37th. Fairness in AI is characterized not by a single metric, but by a spectrum of conflicting objectives. Demographic parity seeks to achieve equal representation of positive decisions across different demographic groups. Equality of opportunity aims for consistent rates of true positives and false negatives. Calibration focuses on ensuring that predicted probabilities are accurate and unbiased within each segment. When base rates differ between groups, it is impossible to satisfy all these criteria at once, requiring deliberate choices and clear documentation of the resulting trade-offs. The available methods for addressing this include pre-processing data, e.g. rebalancing datasets, debiasing features, applying penalties during the model training phase, and adjusting decision thresholds after the model has been trained for specific groups. However, simply ignoring sensitive features does not guarantee fairness, as other features can act as proxies and indirectly introduce bias. In production environments, it is important to implement ongoing monitoring by segment, conduct stress tests on extreme data subsets, establish procedures for appeals, and provide transparent explanations for any rejections. Responsible AI development necessitates a thorough consideration of the specific context, including relevant legal regulations, potential risks to vulnerable groups, and the varying costs associated with different types of errors. The 38th fact states that knowledge distillation and adapters make heavy models practical. The standard method has a teacher model outputting soft probabilities or hidden states, and a student model learning to follow these, often reaching quality that is remarkably similar, but faster and more affordably. There are complexities. Distillation using answers can fixate on incorrect outputs, so mixtures of data sources, validation filters, and self-correction mechanisms are employed. Adapters and LoRa add low-rank updates to specific layers, allowing a single base model to be adapted for dozens of domains without full retraining, which is useful for version control and reverting. A related trend is sparse mixture of experts models, where a router chooses several experts for each token, saving computation for very large total model sizes. Key considerations here are load balancing, routing reliability, and compatibility with attention caches during inference. The outcome is a modular system, a base model, a set of adapters, and a selection policy. Fact number 39. Testing and the ability to observe LLM applications demand new practices. Instead of a single measurement, a range of scenarios is adopted. These scenarios comprise golden prompts with standard answers, sets of data for verifying factual accuracy, resistance to jailbreaking techniques, injections from external origins, and provocations designed to elicit toxic responses. Automated evaluation systems gauge style and adherence to predefined structures, such as rigid JSON formats. Nevertheless, for tasks that are particularly sensitive, the rotation of human reviews remains in place. During the operational phase, runtime, telemetry data is gathered, including the rate of parsing failures, processing speed, cost per token, the frequency of tool invocations, and flags indicating personally identifiable information, PII. Protective measures are established, limits on the number of tokens, time limits, timeouts, a circuit breaker system to manage surges and errors, filters for both input and output data, schema validation, and post-processing steps. Gradual releases, canary deployments, and A/B testing, segmented by task groups, serve to prevent regressions. The practice of logging incidents, along with reproducible repros and documented lessons, is essential for achieving maturity, thereby ensuring continuous improvement of prompts, tools, and policies. Fact 40. In the realm of education, AI has evolved into both a calculator and a coach. Interactive tutors offer step-by-step explanations, modify difficulty levels, create similar exercises, and provide immediate feedback, which is particularly advantageous for language and math studies. Text-based assistants assist with essay planning, drafting, and structuring arguments, but they demand a clear policy on academic integrity, requiring acknowledgement of AI use, citations of sources, and a ban on presenting others' work as one's own. AI aids teachers' in formative assessment by transcribing verbal responses, utilizing rubrics, pinpointing knowledge gaps, and delivering personalized recommendations. It also boosts accessibility through features like closed captions, text-to-speech functionality, and accommodations for dyslexia. Identified risks include AI hallucinations, cultural biases, and overdependence. Therefore, essential standards involve a human in the loop for oversight, fact verification, and the use of open retrieval systems. The most effective strategies involve designing transparent assignments where some tasks are completed using AI as a tool while others are done in a classroom setting without such assistance. Fact 41. A long context is not a panacea. Models can indeed keep tens and hundreds of thousands of tokens in their memory, but attention is distributed unevenly. The beginning and end are prioritized, and the middle gets lost. This is known as the lost in the middle effect. Positional encodings have evolved from absolute to relative and rotary, ROPE. And heuristics like alibi, sliding windows, and sparse attention, where the model only looks at reference anchors, have appeared. In production, a combination is advantageous. Meaningful slicing and headings, extraction of relevant fragments before answering, compression and deduplication, and then careful inclusion in the context with citations. Technically, key value caches and session history reuse help, but injection and contradiction risks increase. The simple golden rule is long context is an expensive resource, so it's better to find what you need first, then read the rest. Fact 42. By structuring its output, a language model becomes a reliable part of systems. When the need arises for JSON, SQL, or an exact function name, simply requesting it is not enough. Decoding must be constrained. In real-world applications, techniques such as context-free grammar, the masking of invalid tokens, strict compliance with JSON schema, and the function calling mechanism are utilized. The latter allows the model to select from a predefined tools and fill in their parameters. It is important to keep in mind that setting the generation temperature to 0 does not eliminate the possibility of incorrectly placed commas. Therefore, iterative processes like generate, validate, correct are implemented, alongside stream validation and limitations on field lengths. Data injections represent a specific risk. Fabricated JSON within a document can either cause the parser to fail or prompt the model to generate text beyond its designated boundaries. Recommended practices include escaping characters, performing initial validation against the schema, providing error reports instead of free text, and using parsing failure metrics as a crucial measure of quality. Fact 43. Corporate AI deployments are fundamentally built on a trust architecture. Before internal documents are connected, DLP and PII retraction are implemented. Secrets are deleted, and access rights are projected into the index to ensure that the output respects ACLs. Serving is isolated both network-wise and logically. Tool keys are stored in secret managers, and third-party plugins operate within whitelists and sandboxes. Observability encompasses not only latencies and costs, but also flags for leaks, toxicity, and policy triggers. Economics are managed through prompt caches, batching, quotas, and context limits. Risks are addressed via appeal procedures, manual review of disputed cases, journaling with pseudonymization, and retention policies. Updates are conducted using canary and A/B methods based on real scenarios, with a rollback plan and fixed control prompts. The most important aspect is change management, reporting on data, versions, prompts, and sources so that any response is traceable to its configuration and time. Fact 44th. Copyright and AI intersect at 3 points: training, output generation, and attribution. Datasets for training have historically been gathered from diverse origins, including materials under open licenses and segments protected by copyright. This makes auditing, license tagging, and data access agreements increasingly important. The challenge of output generation is more complex. Models often overgeneralize but sometimes remember rare segments, like a code snippet or a poem. Risks are lessened through deduplication, filters, and differential privacy. And upon request, checks against reference databases are included. For content origin, C2PA standards and watermarks are being developed, though their resilience to recoding and reshooting is constrained. Legal practices vary by jurisdiction, so a conservative engineering strategy is to keep source links, respect robots and opt out, record data origin, and provide clear descriptions of how the system was trained and is used. Fact number 45. The success of AI is half determined by its interface design. Users need visible guidelines, clear indications of what it can do and its limits, a quick way to reverse actions, a button to check sources, understandable confidence levels, and the status of the tools. Helpful elements include precise or creative modes, previews of changes presented as differences, editable prompts, and short clarifying questions from the system instead of confident but wrong answers. For difficult tasks, a step-by-step progress display with named stages and the ability to step in is important. And for automated processes, a log of actions and a plan before execution. Personal memory is a debated feature. It makes interaction faster, but needs clear rules for saving and deleting information, plus visual signs when it's being used. Lastly, how errors are communicated. Instead of "I can't," it should say, "I couldn't find confirmation. Here are suggestions and sources." This teaches users to interact with AI as a disciplined helper. Fact 46th. Managing data is fundamental to any AI system. When clear rules for data origin, quality, and access are missing, a model becomes a black box that cannot be replicated or secured. The current technology stack features Lineage, which tracks the origin and transformations of every document. Data contracts between teams define schemas, update frequencies, and acceptable data gaps or delays. Monitoring for feature and schema drift is also key, preventing sudden changes in field format or value from negatively impacting predictions. Confidentiality is managed before anonymization through PII removal, masking, pseudonymization, retention policies, and auditable deletion procedures. Replicability is achieved via corpus versions, output hashes, and dataset cards specifying usage restrictions and licenses. In production, SLAs for index freshness, tests for benchmark contamination, and canaries, small, sensitive datasets that detect pipeline issues, are important. Fact 47th. Synthetic data attracts with its scale and speed. Generative models, simulators, and domain randomization enable the inclusion of rare cases, accidents in the rain at night, infrequent diagnoses, or boundary definitions in legal standards. However, synthetic data has a dual aspect. It easily imitates its source, cementing its mistakes, and can alter distributions if it is too smooth. A wise method is to use combinations: a core of real data, synthetic data for the tails, and control groups. Quality is evaluated on three fronts: resemblance to reality, fidelity; utility for the task, utility; and variety, coverage. Protections are added: duplicate detectors, checks for private data leaks, and label validation using external rules. In tabular data, focus is on correlations and rare pairings. In text, on factual accuracy and the absence of junk patterns. The main point: synthetic data does not bypass ethics. The same prohibitions apply to it as to real personal details. Fact number 48. AI systems designed for multiple languages need a localization approach, not simply translation. Difficulties appear from the very beginning with tokenization. Languages that are morphologically rich and the use of code switching result in increased length and errors. Proper nouns, place names, legal terminology, and social undertones frequently lose their significance when directly replaced. Training models further using regional datasets is helpful, but biases from those who annotate the data and a preference for major languages continue to be present. Differences in tone, politeness, forbidden topics, and permissible metaphors are noticeable. In practice, this means segmenting by market, adapting to specific subject areas, compiling dictionaries of terms, and creating style guides for each language. It also involves conducting evaluations with native speakers and performing stress tests using data such as dates, currencies, units of measurement, and address formats. Legal aspects are a separate concern. Rules regarding personal data and content that is allowed to be processed differ, meaning that the oversight of policies and filters cannot be made uniform. They must be understood and recorded at the local level. 49th fact. In the realm of AI, hardware is a contest focused on memory and connectivity. The performance of transformers is more often limited by the bandwidth and latency of accessing weights and KV caches than by flops. This is why HBM, interprocessor exchange buses, and fast internode interconnects are expanding. 2.5D packaging, chiplets, and specialized matrix units decrease the cost per operation. Additionally, 2 to 4 sparsity and INT8/INT4 support are integrated at the hardware level. For distributed training, 0/FSDP and topologies that minimize all reduced traffic are advantageous. In inference, quantization, expert sharding in mixture of experts, and aggressive attention caching are utilized. At the edge, NPUs in phones and laptops are constrained by heat and battery life, requiring modules to be compact and energy efficient. The central trend is the co-design of algorithms and hardware. Models are created with available memory and parallelism in mind, and accelerators are built to match real access patterns. Fact 50. The organizational implementation of AI is a discipline, not a magic button. Teams are put together like a role matrix. Product managers formulate tasks and success metrics. Data engineers and MLOps specialists are responsible for data and pipelines. Researchers are responsible for models and evaluations. Security and legal departments are responsible for risks and compliance. And the red team is responsible for attacks and stress tests. At the management level, a change committee is created, a RACI for decisions is established, and a release calendar with canaries and a rollback plan is made. The economics are calculated in advance: the cost of data, computing, licenses, support, and staff training, as well as the effect: process speed, error reduction, new opportunities. For users, guides, safe interfaces, feedback channels, and appeal procedures are prepared. Most important is transparency, from model and data cards to action logs and prompt versions, so that any response can be traced and, if necessary, challenged. The 51st fact. Federated learning permits model training at the edge on devices such as phones, laptops, and medical instruments without moving raw data to the cloud. The device takes local gradient steps based on its own examples, and the server collects only weight updates. The typical method is FedAV. However, the actual situation is far from the ideal IID condition. Each client has its own accent, camera, and schedule, resulting in data distributions that vary, and lagging participants, stragglers, along with unstable connections, break the round sequence. Gradient compression and partial client sampling are introduced to save traffic. Secure aggregation is employed so the server does not learn the contribution of any particular device. Differential privacy is used to leak through statistics. Personalization tackles the compromise between general and my own by using a common base and then finally adjusting a local head layer. Energy thermal budget and scheduling are separate concerns. Training is initiated at night while charging and conducted in small batches. Fact 52. The standard for dialogue models now involves training with human preferences. Initially, response pairs labeled A is better than B are collected to train a reward model. This is followed by fine-tuning the base model using policies like PPO or simpler methods that directly integrate preferences into response probabilities, known as DPO. The RLAIF approach substitutes human evaluators with a strong judge model, offering cost savings but risking the entrenchment of the judge's biases. It is recommended to mix in human annotations and conduct regular re-evaluations of the judges. A critical point is the fragility of the reward function. Overly rewarding politeness can decrease utility, while strictly enforcing a style can reduce flexibility. Consequently, multidimensional criteria such as usefulness, plausibility, and safety are introduced, along with anti-prompt injection techniques and a policy to refuse dubious prompts. Most importantly, anti-cheating measures are implemented. Logging reward hacking examples, revising instructions, and periodically refreshing data prevent the model from memorizing simple tricks. Fact number 53. In the realm of cybersecurity, AI serves a dual role. It acts as a protective shield and, conversely, as a potential instrument of attack. For defensive applications, AI models meticulously examine logs, identifying anomalous sequences of events. They enhance existing signals by incorporating external contextual information, and aid analysts in developing detectors written in natural language, which are then translated into regular expressions and operational rules. Generative assistants expedite the process of reverse engineering. They provide summaries of functionalities, elucidate network traffic patterns, and offer hypotheses regarding an adversary's tactics, techniques, and procedures, or TTPs. Additionally, code scanning tools are employed to pinpoint insecure coding patterns. At the same time, these very same technological capabilities can be leveraged to create phishing messages, various forms of malware, or obfuscated prompts. The strategic response involves constructing a perimeter of defined processes. This includes employing sandboxes and enforcing restricted roles for technological tools, integrating a human-in-the-loop mechanism for critical actions, deploying red teams to simulate social attack scenarios, utilizing honey tokens and canary artifacts, gathering telemetry data on false positives, and conducting retrospective evaluations. Crucially, a strict prohibition must be enforced against the automatic execution of malicious scripts unless they are properly isolated. 54th fact. Musical models learn through a dual process of sound and symbolic input rather than solely from musical notation. Audio is converted into visual representations known as spectrograms for processing by transformer and diffusion models. Concurrently, MIDI data and tokenized musical scores establish a discrete structure for rhythm and harmony. The generation process is guided by specified parameters, including genre, tempo, key, chord progressions, and timbre references. These parameters enable the creation of accompaniment, the continuation of melodies, and the stylistic imitation of specific historical periods or musical ensembles. A distinct area of development involves the separation of audio into individual stems, such as vocals, drums, and bass. Additionally, neurocoders are utilized for noise reduction and mastering, aiming to achieve a polished final sound for the mix. Key difficulties involve ensuring temporal alignment over extended durations and mitigating subtle attack artifacts in sound that can cause recordings to exhibit unnatural temporal characteristics. This is addressed by combining analysis of local audio segments with global understanding of the musical form. The ethical dimension highlights the necessity of obtaining consent from performers and upholding rights related to music catalogs, with datasets, licenses, and origin information adhering to strict regulations similar to those in text and image processing. The 55th fact: AI and database integration moves past the natural language to SQL paradigm. To stop a system from performing unsafe joins or mixing up amount and quantity, it's provided with the schema, synonym dictionaries, business field descriptions, and examples of correct queries. A strict function calling mode is then activated, where the model only populates parameters for functions like select table, join, filter. Security is handled by read-only roles, limits on row count, time, and cost, a sandbox for subqueries, and default blocking of DDL/DML. For quality, a generate, plan check, explain cycle is used, returning an unaligned plan, too expensive, wrong index, as a signal for edits. Vector indexes are increasingly co-located, enabling hybrid search by meaning and fields, linking queries to schema documentation and data. The outcome is a semantic layer over SQL, letting users see and adjust the logic, not just a nice answer. Fact 56. AI standards and governance are maturing into an engineering discipline, encompassing practical frameworks alongside legal requirements. Organizations are implementing registries for their models, detailing their purpose, data origins, quality benchmarks, and risks. These entries are accompanied by cards specifying constraints, foreseen biases, and safe usage parameters. AI committees are being formed internally, where product, security, legal, and IT personnel collaborate on policies, ranging from data source acceptance to incident management protocols. Risk management methodologies are becoming more prominent, including the identification of harm scenarios, probability and impact assessment, mitigation planning, independent validation, and ongoing audits. International standards for AI risk governance and recommendations from specialized institutes are establishing a common lexicon for defining risks, documenting data sets, and assessing portability. The core aim is to make AI operations reproducible, verifiable, and comprehensible to businesses, regulators, and users. The 57th fact: in finance, AI exists between speed and control. Algorithms rank loan applications, catch transaction anomalies, predict customer churn, and suggest scenarios to traders. Yet, every decision goes through model risk management, independent validation, stress tests, reports on segment biases. Backtests are built with a sliding window to avoid leaks, and strategies are checked for resilience to market regime changes and black swans. Explainability is essential. Regulators and clients can know what factors caused a rejection. Local interpreters, calibration reports, and appeal policies are used. Fraud is fought with graph models and time/device feature ensembles. But limits are set on automatic blocks to avoid freezing honest users. In production, there are 3 lines of defense: the developer, independent model validation, and compliance, with journaling for investigations overseeing everything. The 58th fact highlights AI's role as a core pre-production asset in creative fields. It facilitates the creation of sketches, storyboards, variations for scenes and costumes, and quick set design from text descriptions alongside automated rotoscoping and frame upscaling. Compositing utilizes segmentation, while sound relies on voice synthesis and instrument styling, speeding up animatics and pilot videos. Yet boundaries are essential. An actor's portrayal and voice are legal subjects requiring consent. Synthetic content needs clear marking, and training data must be licensed. Practice establishes rails, distinct areas for generating drafts, manual checks before release, checklists for originality and reference matching, and maintaining the provenance of artifacts. Consequently, AI augments the team, not replaces it, by allowing the review of hundreds of safe options before an artist and director finalize one, informed by human taste and accountability. The 59th fact. In the field of earth science, AI offers assistance where data is highly dynamic across both time and space. Neural networks improve nowcasts, which are brief predictions of precipitation and thunderstorms based on radar information. They also augment numerical atmospheric models by providing swift refinements at localized scales, construct risk maps for floods and landslides, repair missing data in satellite sequences, and elevate the resolution of climate fields for regional planning purposes. Energy providers leverage wind and solar forecasts to balance their grids, and transportation companies use them to optimize traffic and schedules in response to weather. Yet, physics is not entirely surrendered to statistics. Models are validated for compliance with conservation laws and physical limitations, and their outputs are cross-checked with live measurements. The risks include a retuning to quiet historical data and a failure during extreme conditions, which makes stress tests on infrequent phenomena, the use of ensembles, and conservative uncertainty intervals essential for making judicious decisions. 60th fact. AI's development path is shifting towards verifiability and modularity. Investigations are underway into systems where a language model plans solutions as a program, subsequently executing them with tools and subjecting each step to formal verification. This moves us toward evidential AI, which can provide not only a response but also the derivation path. Agentic frameworks are learning to self-constrain via contracts, establishing explicit objectives, permissible actions, budget caps, and rigid interfaces. Simultaneously, the utility of small, specialized models is increasing. These models are fine-tuned with adapters for specific domain tasks and operate locally, adjacent to the data. Large models are functioning as universal task compilers. The significance of hybrids integrating search plus generation plus tools and content provenance protocols is growing. A considerable portion of these developments is not yet robust, with much remaining in active experimentation. However, the overarching trend is unambiguous: a reduction in opaque processes and an increase in verifiable steps and governable decisions. Fact 61. The small language model era revealed that size isn't always the victor. Compact SLMs, with parameters in the hundreds of millions to a few billion range, when expertly prepared with data and instruction fine-tuning, can address whole task categories more rapidly and affordably than giants. The crucial element lies in curated domains, technical support, narrow scheme document analysis, integration into offline applications. They are trained on pristine corporate datasets, learn from distilled examples with step-by-step breakdowns from larger models, and have knowledge transferred via adapters. Benefits include millisecond latency, on-device privacy, and cost predictability. Drawbacks are a sharp quality decline beyond the domain, challenges with infrequent questions, and a greater chance of fragile errors without retrieval aids. A well-developed architecture features an SLM as the engine, accompanied by indices, functions, and rigid JSON output. Fact 62. Confidential computing for AI is advancing across three fronts: trusted execution environments, TEE, multi-party computation, MPC, and fully homomorphic encryption, FHE. TEE involves models and data operating within a secure processor enclave, which lowers the risk of data exposure, even with administrative privileges. This approach is swift but relies on trusting the underlying hardware. MPC distributes a secret across multiple parties, ensuring that no single party can access the original data. It's well suited for collaborative learning in fields like finance or healthcare, but it comes with significant communication costs. FHE permits computations on encrypted data vectors, representing an ideal scenario for private inference, though currently it involves minutes and gigabytes compared to milliseconds and megabytes for open computations. Real-world implementations often combine these methods. Pre-processing occurs in TEE, sensitive features are segmented using MPC, and FHE is applied selectively to the most critical data areas. The 63rd fact highlights AI's role in precision agriculture. Satellite and drone imagery are used to create maps showing plant stress levels. AI models can identify diseases by analyzing the patterns of spots on plant leaves. Moisture and temperature predictions allow for precise management of irrigation and nitrogen application on a field-by-field basis. Tractors are now equipped with visual navigation and weed detection systems for targeted herbicide use, resulting in chemical savings and less strain on the soil. Even simpler technologies are proving effective, such as mobile apps that identify pests from photos, giving farmers an action plan quickly. However, real challenges remain. AI models can encounter issues with new plant varieties or soil types. Sensors may lose accuracy over time. Visual data can be corrupted by shadows and dust. Data transmission in areas with poor connectivity can also be delayed. To ensure success, it is crucial to implement local calibration, retrain models seasonally, integrate a human expert as a digital agronomist in the process, and monitor transparent economic metrics like yield, water usage, and fuel consumption. Fact 64th. Moving trained models to a new domain involves two separate shifts. Covariate shift, where input data changes but the label assignment rule stays consistent, and label shift, where the distribution of classes changes. For covariate shift, feature adaptation and methods that do not require label data are effective. These include aligning distributions, using moments, contrastive objectives, and test time adaptation, which allows the model to slightly modify its normalization parameters based on the incoming data. For label shift, threshold correction and re-evaluation of prior probabilities using unlabeled data streams are used. When facing multiple and rapid shifts, a modular design is superior. This typically consists of a shared encoder combined with lightweight domain-specific heads, replaying past scenarios, and utilizing canary sets to signal any performance degradation. The misconception is that an additional hour of training is adequate. Without diagnosing the specific type of shift, further training may only reinforce existing errors. The correct approach involves measuring the problem, hypothesizing the underlying mechanism, and implementing a targeted adaptation strategy. 65th point. Digital twins enable AI to be used as a proving ground for controlled experiments. Facilities like factories, power networks, storage sites, and even individual boilers are outfitted with simulations that are synchronized with live sensor data. These allow for safe testing of hypothetical situations, new operating procedures, maintenance activities, and pricing models. The models have a dual function. They act as surrogates to speed up physical simulations and help bridge missing data points. Agent-based control loops test various management strategies respecting constraints such as temperature, pressure, and agreed-upon delivery times, SLAs. Crucially, the utility of a digital twin hinges on the precision of its calibration. If not regularly cross-referenced with actual measurements and its uncertainty evaluated, it can foster a misleading impression of command. In practice, there's a need for validation procedures, recording of parameter changes, emergency stop mechanisms for automated processes, and a clear delineation of roles, identifying what the model dictates, what it advises, and when the human operator holds the ultimate authority. 66th fact. Sensor fusion is the nervous system for autonomous machines. Cameras supply color and textures, LiDAR gives geometry ahead for meters, and radar provides range and speed in rain and fog. Inertial sensors and odometry hold the pose, and high-accuracy maps add memory of lanes and traffic lights. Algorithms merge these flows: Kalman and particle filters, factor graphs for simultaneous localization and mapping, SLAM, and priors with uncertainty. Above this, there's object detection and tracking, prediction of pedestrian and car paths, and planning with dynamics and acceleration limits. The difficulty is in the distribution tails: glare, dirty sensors, reflections, rare scene setups. Practice needs a safety case, a list of assumptions, degradation plans, slow down, manual mode, separate braking systems, logging every meter, and regular regression tests for nights, snow, and blocked signs. Fact number 67. Clinical language models are altering the everyday work in medicine where human time is consistently lacking. They can identify a doctor's speech during appointments, gather patient history, organize complaints, point out red flags, create draft reports and discharge summaries, assign diagnosis codes using classification systems, and suggest needed tests. In hospitals, they can summarize records spanning multiple days and create timelines, connecting medications, their doses, and reactions. Importantly, they do not diagnose. That task is for the clinical team. Implementation involves removing personal identifiers from records, keeping access logs, building local datasets with terms, abbreviations, and slang specific to departments, having a human in the loop for all treatment suggestions, and maintaining strict pharmacovigilance. Performance is judged not by blue and rouge scores, but by metrics like time to discharge, the percentage of errors in documentation, and rates of readmission. Automation is not feasible without clinical trials and analysis based on gender, age, and comorbidities. Fact number 68. In the field of law, AI serves as a tool to speed up reading and search processes. Systems are capable of pulling out essential information from contracts, such as the involved parties, timeframes, indemnity provisions, and intellectual property rights. They then compare this information against company policies, pointing out any differences. For e-discovery, models are used to initially categorize large amounts of emails and messages, bringing forward relevant files and unnoticed topics. AI generators can help write memos or summaries of meetings, but every piece of information must be traceable to its source, like a case number, paragraph, or page. To make sure the results are reliable, RAG is used with private collections of past legal cases, along with strict rules for who can access the data and citation chains in the answers. The dangers include the AI making things up, hallucinations, or sounding too sure of itself. Therefore, checks are made on references, the AI is prevented from creating fake case numbers, and records of the instructions given to the AI are kept. The human side of this involves ethics and privacy, keeping client information secret, dealing with conflicts of interest, how data is stored and deleted, and checking for unfairness in suggestions if the AI influences decisions. The 69th fact. Learnable optimization arises at the junction of AI and optimization research techniques. Conventional tasks such as routing, scheduling, and placement are structured as combinatorial challenges with rigid constraints. Neural networks operate concurrently, learning to anticipate effective initial solutions, heuristics, or boundaries for branching. Differentiable solver layers have been created. They are incorporated into the model's concluding stage. Gradients subsequently traverse the complete task, allowing features to learn for the ultimate optimal metric rather than abstract precision. This enhances the speed of vendor selection, warehouse kitting, energy consumption profiling, and material cutting. However, hybrid solutions necessitate strict adherence. Validation against actual limitations like shifts, breaks, and load capacity, the incorporation of robust tolerances for noise, cost estimations for resource reallocation, and the definition of clear SLAs. Moreover, an optimum identified in simulation does not always equate to an optimum in a live system, requiring the deployment of an A/B loop in the production environment and the presence of an emergency stop button for rollback. Fact 70. Artificial intelligence serves as a partner in safeguarding linguistic variety. For languages with scarce resources, data is compiled from radio archives, school papers, newspapers, and spoken interviews. Texts are harmonized based on dialects and recording periods, followed by training for speech recognition and translation, accounting for code switching and loanwords. Linguists construct morphological analyzers and lexicons, while AI models aid in accelerating transcription and marking tones, clicks, and pharyngeal consonants. Practically, community respect and accord are vital. Concerning data ownership, the publication of ritual recordings, and the return of benefits like textbooks, keyboards, and local interfaces. Technical obstacles such as lengthy words, lack of spelling standards, and infrequent proper nouns are managed by adapting tokenizers, cooperative training of kindred languages, and active learning on difficult instances. The threat of homogenization is also present. Hence, dialectal forms are recorded and kept as valuable assets, not as unwanted noise. Fact number 71, AI is now a strong tool for accessibility. It creates alternative descriptions for pictures, makes live captions for talks and meetings, and converts speech to text and back instantly. Keyboards that help users suggest words based on their physical abilities. Models that handle multiple types of information can read charts and screens aloud, spot objects in pictures, and give step-by-step directions for getting around. For people who have trouble speaking, AI builds sentences from picture symbols, AAC, picking the right grammar and tone. Sign languages are difficult. They need 3D tracking of hand shapes and facial movements, and to work well despite different backgrounds and clothes. Models that run on the device itself lower the chances of data leaks. Interfaces follow accessibility rules like WCAG, meaning they have good contrast, clear focus, and descriptions for their parts. There are clear downsides, made-up details in descriptions, cultural differences, and delays from the internet. So, it's required to do user tests with groups of people and use a human in the loop for important situations. Fact number 72. Contact centers serve as a highly developed proving ground for artificial intelligence. The process flow begins with speech recognition and diarization, which identifies the speaker. It then moves to detecting user intent and extracting specific entities. Subsequently, a RAG search is conducted within the knowledge base, and an agent assist function is utilized. This assistance involves providing prompts for agent responses, outlining solution steps, populating CRM fields, and generating automatic call summaries. In real time, algorithms suggest the next best action for the operator. They also measure adherence to scripts and compliance regulations, and they mask personal identifiable information, PII, in call recordings. Improvements are observed in business metrics like AHT, FCR, and CSAT, but with certain limitations. Factors such as speech accents, background noise, embedded codes, and language switching can negatively impact model accuracy. Furthermore, offering direct answers without providing supporting references can diminish user trust. The practical application is a hybrid model where AI offers suggestions and the human operator provides final validation. Essential for integrations is a strict JSON output. Action lists are managed via whitelists, logging is implemented, and regular evaluations are performed on actual calls. Legally, obtaining consent for recording, storing anonymized data, and having appeal procedures for incorrect automated advice are vital considerations. 73rd fact. In sports, AI analyzes play at speeds humans cannot match. Optical tracking and sensors on uniforms gather player paths, speed, and acceleration. This data builds load and injury risk metrics plus individual heat maps. Football uses expected goals, XG, and assists, XA models. Basketball uses expected points models based on defender positions. Computer vision helps with offside calls, automatically makes highlight reels, and tells commentators about play patterns. Coaches get what-if simulations, how pressing changes with a new formation, or the effect of a substitution at a certain minute. The limitations are important. Data isn't always complete. Opponent tactics and style can make models unreliable, and too much personalized risk assessment can unfairly treat players. So, people make the final decisions, and AI is a tool with reports on uncertainty and sources that can be checked. Fact 74th. The battle against deepfakes is essentially a contest between detection signals and methods of concealment. Detection systems analyze a combination of indicators: inconsistencies in how light and shadows appear, small artifacts generated during face interpolation, frequency seams that emerge after image scaling, and misalignments in head posture and distortions in eyeglasses. For audio content, these manifest as spectral anomalies in formants and breathing sounds, along with unsteady speech rhythm. Simultaneously, techniques for verifying the origin of content are being developed, such as C2PA digital signatures and watermarks embedded directly within the creation model, which can withstand repeated encoding processes. However, absolute protection remains elusive, as actions like screen recording, printing followed by filming, and the introduction of noise can all degrade the original signals. A sensible strategy involves multiple layers of defense: employing detectors when content is first submitted to platforms, verifying the sources and associated metadata, involving human experts for particularly important cases, initiating legal actions against the spread of false information, and promoting media literacy skills. For sectors that are particularly vulnerable, such as financial institutions and customer service centers, systems for preventing voice spoofing, conducting active calls, and performing live identity checks are implemented, along with a policy of denying services when suspicions are present. As the 75th fact states, in the context of cultural heritage, AI acts as a tool for detailed examination and restoration, but its application is only effective under expert supervision. AI models can isolate cracks and varnish layers, detect later additions on infrared and X-ray images, compare pigments with mineral composition catalogs, and restore missing decorative elements based on the symmetries of the era. Algorithms are employed to straighten deformed scrolls, read faded text by improving contrast and reconstructing font styles, and join ceramic fragments by matching their edges and patterns. Generative AI can offer potential solutions for missing parts for discussion, labeling them as hypotheses instead of facts. Ethics are fundamental. Original works should not be replaced by synthetic ones. All interventions must be transparent, methods used should be published, and museums and communities must give their consent. The ultimate goal is to carefully reveal the past's layers, not to rewrite it, by minimizing intervention and documenting every restoration step. Fact 76th. Open and closed AI ecosystems are more than just ideological stances. They signify different operational modes regarding risk, development speed, and control. Open weights and code enable result reproducibility, independent verification, quick fixing of vulnerabilities, and support the growth of a plugin and adapter ecosystem. Licenses specify rules for fine-tuning, commercial use, and the requirement for source citation. Closed models provide benefits in optimizing the entire technology stack and in preventing the extraction of training data, but they require trust in the vendor and their internal procedures. In corporate environments, hybrid models are common. An open runtime is used, along with proprietary RAG and index systems, while the main large model is offered as a managed service with service-level agreements and audit logs. Security is influenced by more than just the license. The entire supply chain, including datasets, tokenizers, compilers, and GPU drivers, is subject to versioning and signing. The decision-making process should be balanced and based on specific tasks. For needs involving transparency and portability, open approaches are chosen, whereas for critical requirements like SLAs and scalability, managed services are selected. 77th fact. Within the public sector, artificial intelligence is employed for tasks characterized by heavy and monotonous routine. These tasks encompass the classification of incoming correspondence, the routing of applications, the extraction of specific data points from scanned documents, the summarization of extensive case files, the automated calculation of entitlements, and the provision of guidance to inspectors during field inspections. The demands placed upon AI in this domain are more stringent than those in the business sector. They include the requirement for traceability of decisions, the necessity for explainability of the underlying rationale, robust protection of personal data, and the assurance of the right to appeal. From a technical perspective, this translates to the use of localized data repositories that align with the specific language of the agency, the implementation of strict access control lists, ACLs, governing data indexes, the maintenance of comprehensive access logs, and the integration of human oversight in all processes that affect the rights of citizens. A notable risk involves the perpetuation of historical biases within the algorithms. Should the training datasets inadequately represent certain geographical regions or population groups, the system risks entrenching existing injustices. Consequently, independent evaluations are introduced based on specific segments, alongside procedures for the manual reconsideration of contentious cases, and a policy stipulating no automated rejections without verification. The success of these initiatives is evaluated not by metrics such as BLU, but by the efficiency of service delivery, the frequency of necessary corrections, and the degree of public trust. The 78th point. AI in games acts as anything from a shadow designer to a balance arbiter. Procedural generation crafts game worlds, missions, and dialogue with variety. Large language models give NPCs the ability to speak, remember past meetings, and have their own drive, making their actions less formulaic. Bot testers execute millions of simulations to find economic exploits and level bugs. Systems track telemetry and change game difficulty based on the player. For security, AI finds cheaters by looking at input oddities and physics mismatches. The dangers are evident: bad content in user requests, surprising AI answers, and high server use for long chats. Safety measures are filters, allowed topic lists, safe patterns, local small language models, SLMs, for quick reactions, and strict context caps. AI's creative talent shows when it doesn't replace game design, but creates room for choices and real-life small things that artists and writers then pick and perfect. Fact 79th. Within materials and chemistry, AI is propelling inverse design. The approach shifts from prolonged searching to first defining target properties, such as strength, thermal conductivity, or absorption bands. Models then suggest candidate materials exhibiting the optimal trade-off. Generative networks are employed to design molecules and crystal structures. Predictors assess stability and toxicity. Synthesis planners map out reaction sequences. Active learning directs experiments to areas where knowledge expansion is greatest. Laboratories are becoming automated, with robots dispensing reagents and spectral and diffraction data being fed directly into models for hypothesis refinement. Key limitations involve data fragility, a lack of negative results, publication biases, and the disconnect between theoretical stability and actual synthesizability. Thus, validation cycles are crucial, involving in silico, in vitro, in vivo/in operation phases, alongside reproducibility protocols and error logs. This enables the model to learn from both successes and failures. Fact 80. Secure software development leveraging AI is essentially SSDL amplified. While AI assistants expedite coding, they also enlarge the attack surface. The engineering framework mandates policies for AI-generated code, including required tests, linters, and type enforcement. This also entails verifying licenses and the source of code snippets, conducting static vulnerability assessments, employing secret scanners, and establishing a repair loop where a failed test serves as input for the model. On the delivery side, SBOMs and artifact signatures are put in place, with AI assisting in dependency validation and the identification of supply chain injections. Infrastructure practices involve isolated sandboxes for running model code, roles with minimal permissions, logging of tool usage, and a prohibition on network activities unless explicitly whitelisted. Culture plays a vital role alongside technology, featuring prompt guides, examples of blacklisted anti-patterns, periodic red team engagements, and success metrics measured by bug closure rates, incident reduction, and recovery duration rather than by lines of code produced. Fact 81. Search engines are transitioning into answer engines, where generative models are incorporated on top of indexing, not as replacements. The foundational steps remain familiar: crawling, deduplication, analysis of links and data schemas, schema.org, passage extraction, and ranking by quality signals. Following this, RAG is activated. Fresh paragraphs are retrieved based on a query, cited with source attribution, and a language model crafts the response, maintaining links and timestamps. Key threats include LLM spam online, prompt injections directly on pages, and fact drift. Protective measures include trusted domains, penalties for unusual patterns, citation verification, and sandboxing for tools. Metrics are being redefined. Instead of measuring clicks, they measure the time to the first useful snippet, the rate of questions with verified sources, and resistance to manipulative sites. For content creators, this represents a paradigm shift. Structured content, clear main points, and verifiability are paramount, superseding mere volume. Fact 82nd. AI in recruitment serves as a structured verification process with high stakes. Resumes and applications are processed into key attributes: skills, tenure, domains, and certifications. This information is then aligned with competency dictionaries and job descriptions. Chatbots assist by suggesting interview questions and recording candidate responses. However, legal regulations are rigorous. In many regions, automating hiring decisions is deemed a high-risk activity. This necessitates that decisions are explainable, that biases are monitored, and that candidates have the right to appeal. Technically, this means employing clear indicators, e.g., not using proxies for gender, race, or age, generating calibration reports for different user segments, performing regular evaluations on anonymized datasets, and retaining records of the factors that led to a decision. It is considered good practice to have a human review every rejection, to prohibit blacklists without verifiable justification, and to manage personal data leaks and storage durations. Companies that focus on accurately identifying potential and providing fair feedback, rather than simply filtering by keywords, achieve better results. The 83rd fact states that power systems are transforming into digital organisms, where artificial intelligence helps maintain a balance between energy generation, the grid, and demand. In short, forecasts for wind and solar power generation are used to optimize the scheduling of generating units and economic dispatch. Models designed to detect anomalies monitor phase angles and frequency using data from PMU sensors. For flexible demand, policies for demand response are developed, covering everything from smart thermostats to charging electric vehicles during off-peak hours. Agent-based systems are employed to test maintenance schedules, ensuring that the N-1 criterion is not violated, and digital twins help pinpoint network bottlenecks. The risks associated with this include unforeseen weather events, referred to as black swans, and cyber attacks. Therefore, decisions are not fully automated. An uncertainty interval is factored in, protection relies on established relaying principles, manual control procedures are implemented, and a degradation plan is created. Ultimately, AI does not manage the electricity itself, but rather proposes plans that can be checked, which the dispatcher then approves, taking into account market rules, safety considerations, and the actual condition of the equipment. Fact 84th. Biosecurity in the era of generative models necessitates guardrails at each juncture, ensuring that knowledge contributes to healing rather than causing harm. A properly designed architecture precludes the provision of detailed protocols and hazardous procedures. This is accomplished through lexical filtering, maintaining lists of prohibited queries, validating links to authoritative sources, and excluding datasets with sensitive instructions during the training phase. Red teams, comprising biologists, evaluate models for attempts to bypass restrictions. Additionally, a human-in-the-loop policy establishes that all recommendations are exclusively for professionals and must cite clinical guidelines. External to the models, industry practices govern the screening of orders for synthetic sequences, laboratory audits, tracking data provenance, and ensuring transparency in research objectives. The fundamental principle is that AI functions as a tool for generalization and search, not as an experimentation textbook. Safety and ethics are primary, even if it means refusing to provide answers. Fact number 85. The job market evolves not suddenly or by profession, but by the tasks performed within job roles. AI speeds up routine activities, from creating draft emails and summaries to initial data and code analysis, thereby freeing up time for client contact, design, and hypothesis verification. Studies reveal a rise in productivity for tasks with a standard structure. However, this also brings a risk of pseudo-efficiency, where the quantity of pages or code commits increases but the quality of solutions decreases. Thus, Centaur process designs are favored. A person sets the goal, AI proposes options, and the person reviews and makes the final decision. Furthermore, metrics should focus on results, not volume, such as defects, NPS, closed incidents, and cycle time. Crucial skills include task setting, working with information sources, managing tools, and taking responsibility for the final outcome. Employers need retraining programs and a clear policy on AI use. Employees need to develop the habit of documenting their conclusions and be able to explain potential errors made by the model. Fact 86. In the field of logistics, AI acts as a manager of hidden flows. It forecasts demand for hundreds of product items, SKUs, develops what-if scenarios for promotions and seasonal variations, optimizes the distribution of inventory between warehouses, and resolves routing tasks by considering time windows and constraints on weight and temperature. The models analyze telemetry data from trucks, AIS signals from ships, traffic jam data, and weather conditions, providing advance notification of port congestion and overloaded hubs. Internally, a full ensemble of algorithms is at work. Gradient boostings and transformers for forecasting, MILP/CPSAT and heuristics for planning, graph networks for identifying bottlenecks, and anomalistics for fraud and loss detection. The risks are genuine. The bullwhip effect magnifies errors, distribution shifts compromise calibration, and rigid optimization based on theoretical calculations disregards the human element, shifts, safety, and fatigue. Mature technology stacks include additional buffers, intervals of uncertainty, digital twins of supply chains, and key performance indicators, KPIs, that cover not only service-level agreements, SLA, but also emissions and returns. Fact number 87. In the field of mental health, AI functions as a support layer, not a therapist. Assistants assist with thought journaling using CBT principles, offer breathing exercises, remind users about medication, and track sleep and activity patterns. Language models can gently rephrase catastrophic thinking and provide informational materials. Risk algorithms detect crisis markers in text and speech, such as sharp changes in affect, mentions of self-harm, or long pauses. Important boundaries are in place. These systems do not diagnose and do not replace a human specialist. In dangerous situations, they must clearly direct users to licensed services and hotlines, store data with consent and minimal collection, and exclude advice outside standardized protocols. Cultural and language nuances are crucial, as the same word carries different meanings in different settings. Reliability is measured not by the niceness of the dialogue, but by user retention, symptom reduction on validated scales, and safety. The 88th fact. In the fields of architecture and construction, AI is speeding up the progression from conceptual sketches to the point of being put into use. Generative design evaluates numerous layout options based on specific requirements, including solar exposure, escape routes, structural frameworks, and acoustic qualities, suggesting balanced solutions concerning floor space, expenditure, and inhabitant well-being. BIM models augmented with AI can identify conflicts between different engineering services, predict the likelihood of timeline overruns through 4D/5D analysis, and gauge the effect of alterations on budget forecasts. At the actual building site, computer vision technology, utilizing data from drones and cameras, cross-references the current state of construction with the planned schedule, oversees the wearing of personal protective equipment, PPE, and tracks areas of potential danger. Risk prediction models provide warnings about probable delays in the delivery of building materials. Within the buildings themselves, digital replicas and forecasting analytics optimize the performance of HVAC and lighting systems, resulting in reduced energy consumption. There are notable limitations: the standard of the initial design drawings, inadequacies in building codes, singular structural connections, and the manual workarounds employed by contractors. For these reasons, the ultimate decisions are made by the architect and the technical inspection team, with AI acting as an advisor that provides a clear record of the basis for its recommendations. It is the 89th fact that in the field of journalism, AI has become simultaneously a magnifying glass and a shovel. It meticulously examines extensive collections of documents, records of meetings, and financial budgets, swiftly generating chronological sequences and diagrams of connections. AI also supports OSINT investigations by correlating shadow positions and solar angles for the purpose of geolocation, comparing the outlines of equipment, and identifying registration numbers and emblems. Multimodal AI models are capable of extracting significant frames and potential editing markers from video content, while synthetic media detectors are designed to find artifacts indicative of deepfakes. The generative capacity of AI proves valuable for producing preliminary drafts and compiling sets of questions. However, it is imperative that every factual claim is accompanied by a citation and points to its original source. Editorial policies expressly forbid the inclusion of invented quotations and the automatic release of material without thorough verification. The inherent risks include AI hallucinations and a tone of certainty that may misrepresent an assumption as a factual reality. Protective measures include employing retrieval-augmented generation with trusted data repositories, maintaining a citation chain within the written content, and conducting a two-step verification process involving both the author and an editor. Ethical principles demand transparency in the utilization of AI and a steadfast respect for individual privacy and the presumption of innocence. Fact 90. Laboratories are now seeing the development of self-driving scientific circuits. In these setups, artificial intelligence plans experiments, robots dispense reagents, sensors immediately output spectra and curves, and Bayesian optimization or active learning chooses the next action to maximize knowledge. This process speeds up the search for catalysts, electrode materials, and drug formulations. Surrogate models substitute for expensive simulations, and digital notebooks log all hypotheses and parameters. However, this is not magic. Without negative results and reproducibility checks, circuits can learn to find only easy wins. Sensors can drift, and a simulation's correct maximum might be a synthesis dead end. Therefore, blind validations on different equipment, uncertainty intervals, protocol pre-registration, and safety red buttons are employed. The aim is not to replace scientists, but to expand their reach and perception. to shorten the hypothesis-to-verification cycle and truthfully record the path to discovery. Fact 91. Quantum computation and AI are coming together in hybrid designs, where sections of a problem are solved using different physical frameworks. Variational quantum algorithms are employed to train a compact, adjustable quantum circuit so that its results reduce a classical cost function. The adjustment of parameters is done on CPUs, GPUs, while the actual expected values are measured by a quantum apparatus. Within machine learning, this appears as quantum kernels, which substitute quantum similarity into SVMs, alongside feature creation and the modeling of quantum chemistry, leading to refinement into classical networks. Actual limitations are present: noise, a low count of qubits, loss of quantum state, and random measurement errors. For this reason, error mitigation techniques averaging over various circuits, compilation matched to the device's structure, and careful comparisons against powerful classical approaches are implemented. The closest practical utility lies in niche tasks where physics offers an advantage in feature expression, and AI manages the experimental process and processes the outcomes. Fact 92. A smart city equipped with AI operates as a series of connected functions. Traffic lights that adapt to traffic conditions help shorten queues through the prediction of traffic flow. Computer vision technology is used to count passengers and identify areas of congestion. Models that forecast demand adjust the schedules for public transportation in response to events and weather patterns. In the realm of utilities, digital twins of buildings are employed to predict heat loss and to regulate heating, ventilation, and air conditioning (HVAC) systems on a zone-by-zone basis, which in turn reduces peak consumption. Routing algorithms are utilized to optimize the collection of waste, relying on data from sensors that measure the fill level of containers. At the security level, AI is capable of detecting anomalies within infrastructure networks and identifying water leaks. It is essential, however, that the architecture be ethically centered. This involves minimizing the collection of personal data, implementing data aggregation and anonymization techniques, prohibiting mass identification without valid legal reasons, and ensuring the availability of open reports detailing metrics and any identified errors. The technical framework should include verified datasets, stress testing for unusual scenarios, resilience against communication failures, and manual control modes for operators in the event of system disruptions. Fact 93. Predictive maintenance transforms noise and vibrations into early signs of malfunction. Sensor data, including spectra, envelopes, and windowed statistics, are collected. These features are then input into gradient boosting or temporal transformer models, which calculate the remaining useful life, RUL, and the probability of failure. For turbomachinery and conveyors, the rise in side harmonics, phase skew, and temperature drifts are observed. In electrical grids, frequency responses and partial discharge surges are monitored. Trust is built upon baselines of normal operational states, threshold calibration for different work modes, and post-repair checks to ensure the model detects recovery. Risks involve false alarms, changes in part names, and sensor degradation. Therefore, signal quality control layers, Bayesian uncertainty intervals, human verification before shutdowns, and an economic function for error costs are implemented, as delaying repairs can be more beneficial than a false line stop. Fact 94. Astronomy and space operations utilize AI when data volumes reach record levels. Algorithms search for exoplanet transits in light curves, filter out systematic telescope noise, and classify supernova by photometric features. In radio interferometry, networks solve inverse problems for image reconstruction. And on satellite images, vision systems assess forest fires, ice melt, and urbanization dynamics. For space traffic, AI helps track objects by radar and optical paths, merging observations from different sources and estimating collision probabilities. Planners optimize maneuvers with fuel savings and communication constraints in mind. It is critical to consider false positives and incomplete object catalogs. Decisions are verified by astronomers and controllers, and models are supplied with confidence scales and reproducible metadata, from calibrations to pipeline versions. Fact 95th. Personal knowledge and AI come together in a second brain. This system uses embeddings, retrieval, and generation to form an active layer over notes and documents. Notes are segmented into chunks, indexed with vectors, and a conversational AI responds with citations and links connecting notes by topic and date. Beneficial applications include automatic meeting summaries, task extraction for checklists, table of contents generation, and concept maps with who, what, when navigation. Risks include false memories from inaccurate links, data leaks during cloud synchronization, and the merging of private and public data. To mitigate these risks, practices such as local indexes, encryption, clear source indication in every answer, note versioning, and a changelog are advised. To prevent over-reliance on automation, rituals are established, weekly reviews, manual tagging of key ideas, and archiving outdated content. The AI functions as an editor and navigator, but the owner retains final accountability for the structure and meaning of their personal knowledge. Fact 96th. On the frontier where AI meets neurointerfaces, active efforts are focused on translating intentions directly from brain signals. Electrocorticography and single neuron recordings offer robust data for controlling artificial hands, allowing models to learn grasp, rotation, and force by recognizing spike patterns. Non-invasive methods like EEG/MEG offer less precision but are functional for cursor control, letter selection on a matrix, and basic communication for those with locked-in syndrome. Training involves calibration sessions that account for electrode shifts and user fatigue, followed by a feedback loop, visual or tactile, to help the user adapt to the device. Current experimental systems can convert imagined speech into text, and visual prosthetics translate scene outlines into sensory stimuli. Significant challenges remain, including individual brain variations, data integrity, ethical concerns, and the privacy of thoughts. Thus, NeuroAI is presented as a supportive technology requiring expert supervision. Fact 97th. The coordination of robot and drone swarms is a real-time AI challenge involving dozens of units tasked with scouting, moving, collecting, and avoiding collisions. Control is structured in a layered manner. Local rules for avoiding obstacles, like potential force fields and barrier functions, are combined with global planning based on graphs and task assignment through matching. Multi-agent reinforcement learning is used to develop cooperative policies, ranging from distributing roles to passing a mission objective to the nearest unit. Given that communication can be unreliable and sensor data may be lost, system architectures are designed to be resilient to delays and packet loss, and protocols are made robust against leader disconnections. Safety is a critical requirement, implemented through geofences, defined flight corridors, backup parachutes, strict speed limits when operating near people, and the option for manual override. Domain randomization is essential for transferring models from simulation to the physical environment, accounting for variables such as wind, lighting conditions, and noise from inertial measurement units. Applications include warehouse inventory management, power line inspections, search and rescue, and delivery services. Each flight, however, must comply with established rules and be documented in a telemetry log. Fact 98. In the telecom sector, AI is functioning as the autopilot for radio networks. It forecasts traffic by hour and by region, dynamically adjusts slot schedules and modulation types, and manages the beams of massive MIMO systems, adapting their directional patterns to mobile subscriber groups. RANs are integrating self-tuning capabilities, automatic cell parameter selection, compensation for signal overlaps, and the search for silent interference. At the transport layer, models identify anomalies in delays and packet loss, suggesting rerouting options. At the network edge, AI distributes resources among AR, VR streams, games, and industrial IoT, respecting SLAs for various network slices. A network digital twin is also appearing, a simulator where AI tests policies before activating them in live operations. The main challenges are the portability of solutions between cities and vendors, fairness for subscribers at cell boundaries, and compliance with protocol standards. Therefore, solutions go through sandbox testing, canary deployments, and engineer monitoring. 99th fact: verifiable AI is an emerging field where accuracy, coupled with cryptographic proof of step-by-step correctness, holds significant importance. ZKML endeavors to encapsulate the inference process of a model into a compact proof, SNARK-STARK. This allows an independent party to ascertain that a model, using hashed weights, has indeed produced a particular response to a specific input, without revealing those weights. This is advantageous for outsourcing computations and for model markets, though it presently entails substantial time and memory costs. As a result, hybrid methods are adopted, such as Trusted Execution Environment (TE) attestation, signatures on weight and tokenizer versions, and checks for cache integrity. Simultaneously, the development of watermarks for weights and outputs, origin records, and training logs that document datasets and operations is progressing. The core concept is that responses must be not only plausible but also subject to verification, utilizing hashes, signatures, schemes, and computation trails, while managing the trade-offs between privacy, speed, and cost. Fact 101. The hardest AI tasks are still open. Dependable multi-step reasoning without confidence errors, planning over long horizons considering constraints and information cost, grounding knowledge in physical experience, and causality instead of correlations. Models lack stable memory without forgetting and generalization capabilities beyond training distributions. Safety relies on robustness to attacks and the ability to honestly estimate uncertainty. Evaluation is also a challenge. Benchmarks get old, leaks and overfitting to tests distort the picture. And real-world metrics, cost, latency, share of verifiable links, impact on people, require observability discipline. So, the path is clear. Less magic, more tools, logs, verifiable steps, and human control where the cost of error is high. AI is growing as an engineering system with frameworks, protocols, and accountability.